Hello and welcome to the MATLAB and Simulink Racing launch. In this video, we'll showcase the model of a basic motor cooling system, drawing inspiration from automotive student competitions as a point of reference. We will first sketch the system layout of the cooling system and then mimic it in Simscape, which enables you to rapidly create models of physical systems within the Simulink environment. If you are new to Simscape, we would encourage you to go through the Simscape on-ramp, which will help you to understand the basics of modeling dynamic systems in various physical domains. Also, the models that we are going to demonstrate are freely available on GitHub, and the link can be found in the video description. Now let us understand the motivation behind building a cooling system. Imagine the intense atmosphere of an electric automotive student competition where the crucial aspect that teams focus on is improving the performance of their vehicle. However, under high performance driving, electric motors generate a significant amount of heat, and effectively managing this heat is essential for optimal performance. Now, to keep their motors cool and maintain peak performance, teams employ innovative cooling systems. They integrate high performance radiators with advanced airflow management techniques, ensuring efficient heat dissipation. The cooling system design not only keeps the motor cool but also enhances the overall efficiency and reliability of the electric vehicle. Now, with this strong motivation from an automotive student competition, let us now sketch a simple cooling system architecture. So, this is our motor where heat dissipation takes place through conduction and convection, which can be represented in the form of a thermal equivalent circuit. In the cooling system, we start with a tank that serves as a reservoir for the liquid coolant. Then, the coolant is propelled by the pump, which maintains a continuous flow. Further, the next component is a radiator that acts as a heat exchanger for the heat transfer from the coolant to the surrounding air. Plus, the fan enhances the airflow, increasing the cooling efficiency. Once the coolant has been cooled down in the radiator, it is directed to the electric motor. Now, as it flows through the motor, the coolant absorbs the heat generated by its operation. And finally, the heat coolant is returned to the tank. This ensures that the motor remains within the desired temperature range, preventing overheating and maintaining optimal performance. So now that we have a system layout, let us mimic this physical system layout of the cooling system in Simscape. For this, we'll use an electric vehicle model that tracks a reference drive cycle. For example, we have referred to one of the Formula Student drive cycles in this case. The model consists of a drive cycle source, a controller subsystem, a vehicle subsystem, and a visualization subsystem. Further, the vehicle subsystem comprises of a longitudinal vehicle dynamics and an electric motor. The Simscape motor and drive block represents a generic motor and drive operating in torque control mode or equivalently current control mode. As we have to implement a cooling system for the motor, we will activate the thermal feature to create a thermal port H. The port H represents a thermal conserving port associated with the temperature and heat flow. For a clear visual representation, we have created an empty subsystem consisting of only H port, and in this empty canvas, we will mimic the physical system layout of the cooling system. So let us get started and build with us. Referring to the system layout that we sketched earlier, we use the conductive heat transfer and convective heat transfer to define the heat dissipation. In these thermal elements, A and B represent the thermal ports. Also, note that the heat flow is positive if it flows from A to B. Further, we add a temperature source to represent the environment temperature and the thermal mass to represent the internal energy. So as you see, this part mimics the thermal equivalent circuit. Further, we will model a thermal liquid container using a tank block. Please note, while searching for the relevant blocks, you will see TL, which means it represents a thermal liquid. Now, let us get back and change the number of inputs of the tank to 2. One is to connect the pump and another to take the fluid back from the motor through the pipe network. As we are assuming no heat transfer through the tank wall, we'll insulate the thermal port by connecting it to the perfect insulator block. The other ports are to measure certain properties that we don't need currently, so we will terminate these signals by connecting them to the PS terminator blocks. Next, we connect the port B to the inlet of the fixed displacement pump, which is rotated at a certain angular velocity represented by the ideal angular velocity source block. The port C of the pump is associated with the pump case, hence we will connect rigidly to a rotational reference. Then we will add a heat exchanger to transfer heat between the gas and the thermal liquid network. In this block, ports A1 and B1 are the gas conserving ports associated with the heat exchanger inlet and outlet for gas, whereas ports A2 and B2 are the thermal liquid conserving ports associated with the heat exchanger inlet and outlet for thermal liquid. For the flow of the thermal liquid from the pump to the heat exchanger, we'll connect the outlet of the pump to the inlet of the heat exchanger. Further, for the airflow inlet to the heat exchanger, we need a fan. So, we connect the fan and the heat exchanger. And as the fan is exposed to the atmosphere, we will connect the inlet of the fan, port A, to a reservoir, and then we will rigidly fix the fan. Like the pump, we'll also rotate the fan at a certain velocity and will make the necessary connections. As outlet port B is exposed to the atmosphere, we will connect it to a reservoir. Next, we will add a thermal pipe to represent the pipe network associated with the motor. Then, connect the thermal port of the pipe to the motor's thermal port, and after connecting it to the outlet of the heat exchanger, we will finally dump the hot fluid back into the tank. So, this completes the steps to mimic the system layout of the cooling system. Now, before we finalize the model, we'll define the fluid properties to define the thermal liquid properties and similarly the gas property. This can be easily done using the fluid properties blocks. Then, we add a temperature sensor to measure the temperature of the motor and a flow rate sensor to measure the flow rate. Please note that while building the model, we have simplified the video by avoiding a detailed explanation of each variable required in these blocks. However, if you are interested, you can visit the GitHub link to download the model, or if you have a data sheet for your components, you can use that as a reference to define the variables. So here we already have a pre-built model with all the variables defined, and now when we run the model, it is evident from the result that the motor temperature is under control when the cooling system is implemented. So this not only keeps the motor cool, but can also help you enhance the overall efficiency and reliability of your vehicle. In just a few minutes, you saw how you can easily mimic the system layout into a model using Simscape. We used an electric vehicle model as a reference, and for a certain drive cycle, we kept the motor temperature under control. So what next? Well, you can use this learning to build a more complex model depending upon your requirements. For example, you can replace a system level model with a detailed motor and motor controller model. Further, you can try different cooling system layouts referring to some of the advanced examples. You can use parameter estimation to size the pump, radiator, fan, or other sensitive components. Also, you can develop a controller to turn on the cooling when needed. So give it a try to better design your vehicle, and in case of any queries or suggestions, please feel free to reach out us at racinglaunch@mathworks.com. Thank you.